Hello. In this video, I'm going to give an introduction to projectile motion, which means just two-dimensional motion near Earth's surface, where gravity is pulling down towards the Earth's surface. You can see a little picture that I've drawn here with a rough trajectory. So, some rock is being thrown by a person, and it kind of takes the trajectory shown. I've also at the top here written our way of splitting this two-dimensional problem into two one-dimensional problems. So the general way that these sort of problems are approached is to deal with the x-axis separately from the y-axis. So if I've got x horizontal and y vertical, then I can write a displacement in the x-coordinate and a displacement in the y-coordinate. To do that, I would need to know an initial x velocity, an initial y velocity, and some acceleration in the x direction and some acceleration in the y direction. Typically for these problems, the x acceleration will be 0, and the y acceleration will be gravity. And we'll see how that works a little bit later on. I've also rewritten in a slightly different form where I've broken the displacement into a final position minus an initial position. So the position at some given time is equal to an initial position plus a displacement in both cases. So this video is going to be about how to do this when you have a velocity that doesn't point purely in the x direction or the y direction. Oops. So if I look at this rock, the way that the rock is moving at the beginning of its motion is kind of like this way. And that arrow is meant to represent the way it's moving at the beginning of its motion. So another way to say that is I know that its velocity is pointing in the direction shown at the beginning of its motion. The velocity, the way that the rock's moving, its velocity will change direction as it moves. So for example, at the top of the arc, the velocity would be moving, kind of purely horizontally. And then somewhere on the downward slope, it's moving kind of pointing downwards there. But at the beginning, I can say it has some initial velocity. And I'm going to denote that with VI and this vector hat on top. So this is to say VI is a vector here. And this little hat on top tells you that I'm talking about a vector rather than a scalar speed or something like that. And what that means is VI, this quantity, is a two-dimensional vector. That means that some part of it points in the x direction and some part of it points in the y direction. The length or the magnitude, length of the vector, or the magnitude, we might call it, is the speed. So that is how long this arrow is, tells you how fast the rock is moving at the point that we've chosen at the beginning of its path. So if the vector is longer, that means faster motion. If the vector is shorter, that means slower motion. And the direction of the vector is just how it's traveling at that moment of time. So the direction shows the direction of motion at some particular time, which will change over time as the rock moves. So as I said, and as we've talked about, the goal of a two-dimensional problem is to split it into two one-dimensional problems, one that's an x-coordinate problem and one that's a y-coordinate problem, and then use that to figure out what you want to figure out. The tricky bit is taking something that looks like this, that is not purely x or y, and splitting it into something that can be represented in the x and y direction. So the way we do that is with a little bit of vector math, which really boils down to triangles. So I'm going to draw a picture here. So if I have, here's my rock here, let's say. I guess maybe I should make that this color. If I draw this velocity vector, it's an arrow that goes this way. And the length of that arrow is the magnitude of the vector. I can write that magnitude like this. So these little bars represent magnitude. And all that means is that instead of being a vector now, it's just a length. So if I had the speed, the length of this arrow would be the speed, and this quantity represents the speed. What I'm going to do, or what I'm going to claim, which turns out to be true, is that I can make a triangle that looks like this, a right triangle, and one side of this triangle points entirely in the y direction, and that length will correspond to the initial y velocity. This length, or this side of the triangle, which points entirely in the x direction, that length corresponds to the x velocity, in this case, the initial x velocity, because I'm talking about an initial velocity. And our goal will be to figure out what these side lengths are of this triangle. This is a little bit abstract because I'm talking about not a physical triangle in space, but a triangle that represents speed or velocity on each of its side lengths. So I'm looking at a triangle where the units of each length are meters per second here. And what the things represent are this side length is the initial y velocity, and this side length is the initial x velocity. And those side lengths will depend on what the length of the hypotenuse of this triangle is, and also what angle this triangle is at relative to the x-axis or the y-axis. I'm going to define an angle here. I'll call this angle theta. And so depending on what theta is, Vx and Voi will change even for the same speed here. So if the angle is really low, like this, let's say, you can see that Vy is small, but Vx is big, which makes sense because the closer that you get to horizontal, the lower the angle is. The closer the initial y speed velocity gets to 0. And if I have a really large angle, that is an angle close to 90, then you've got not very much x velocity, but a lot of y velocity. So that is the closer that the angle gets to vertical, the closer the initial x velocity gets to 0. So that kind of makes sense. So these values, Vxi and Vyi, will depend on what the speed is and what the angle is. So depending on that angle theta, there's specific relationships between the side lengths of this triangle that tell you what the relationship is between the hypotenuse, the opposite side, and the adjacent side. So let me define a few more things here. I'm going to draw another triangle. So if I take this triangle and redraw it. So let me copy this, paste it here. So I've got another triangle, and now just more abstractly, in any given triangle, right triangle like this, I'm going to define the hypotenuse as this longest side length, and then the adjacent side here, that's the side that's next to the angle. And then this side here is the opposite side. That is the side opposite to the angle that we have. And depending on the angle, there are specific relationships between the opposite side and the hypotenuse and the adjacent side and the hypotenuse. So here's a few examples. So for example, if theta is equal to 30, the triangle looks like this. So something like this. And it's not a perfect triangle, but I think you get the idea. So if I say there's a 30-degree angle here, if I just let the hypotenuse be equal to 1, as an example here, then if the hypotenuse is 1 and the angle is 30 degrees, then the opposite side is equal to 1/2, always. And the adjacent side is equal to √3/2. √3 is about 1.7. So √3/2 is about 0.866 or so. And it will always be true that the ratio between the opposite side and the hypotenuse for a 30-degree triangle like this will be 0.5. the ratio between the adjacent side and the hypotenuse will always be √3/2. And the ratio between the opposite side and the adjacent side will always be equal to 1/√3. So, for example, if I scaled this triangle and I made the hypotenuse 2, then the opposite side becomes 1 and the adjacent side becomes √3. But the ratios between the sides stay the same. So proportionately, it scales proportionally on all sides, which is probably intuitive. And so these are just known values. People have been studying triangles for a long time, and these are the values you get for the side lengths. So those relationships in the triangle stay the same, always. Another example, if theta is equal to 45 degrees, then the triangle looks something like this, where the side lengths are the adjacent and opposite side lengths are the same, symmetrical. So 45 degrees here. If I let the hypotenuse be 1 again, then as it turns out, both side lengths are √2/2. So √2 about 1.4. So the side lengths somewhere around 0.7 or so. So the relationship between the opposite and the hypotenuse, that ratio, will always be √2/2. Same for adjacent and the hypotenuse, that ratio is always √2/2. And the ratio between the opposite side and the adjacent side, that's just equal to 1, which is kind of interesting, which makes sense. The side lengths are the same, so their ratio is 1. These ratios change depending on the angle. So they're functions of the angle. These ratios, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, they're given special names, but they're just meant to represent the ratio, these side length ratios at different angles. So these, let me just scroll down. So these ratios are defined as these sort of special functions. They're defined as sine, that's opposite over hypotenuse, cosine, that's adjacent over hypotenuse, and tangent, that's opposite over adjacent. These are important trigonometric functions. For us, though, they're really just ways to shorthand write these ratios. So, for example, for my 30-degree triangle, the opposite over hypotenuse ratio, that's the same thing as the sine of 30 degrees. Sine of 30 is 0.5. The adjacent over hypotenuse, that's the same thing as cosine of 30. So cosine of 30 is √3/2. And opposite over adjacent, this is the tangent of 30, is 1/√3. And same here, opposite over hypotenuse here, tangent, not tangent, sine of 45 degrees is √2/2. Cosine of 45 degrees is √2/2. And tangent of 45 degrees is 1. So these are functions on your calculator. So if you plug in sine of 30, you have to make sure you're in degree mode on your calculator rather than radian mode. We can talk about what that means if you want. But if you're in degree mode and you plug in sine of 30, it'll tell you 0.5. And what that means is that in a triangle like this one, the relationship between the opposite side and the hypotenuse, that ratio is 0.5 always. Okay, that's pretty abstract, but I want to show you an example of how you actually use this to solve the problem that we wanted to solve, which is how you break down that velocity vector into the x part and the y part. So let me set up that example next. Okay, so I've copied the picture from the top of the last page, but now I have some specific values here. So if I have my initial velocity vector points up like this, now I'm saying the magnitude of that initial velocity vector is equal to 20 meters per second here. So the speed that I throw the rock with is 20 meters per second. And also I'm saying that I throw it at an angle 37 degrees above the horizontal. So that gives me a specific triangle to work with. So if I draw a triangle, here's my velocity vector, and I can make this triangle with some side in the y direction and some side in the x direction. So there's a right angle there. So the length of the hypotenuse is 20 meters per second. That's the length of the vector. How long that vector is the speed, 20 meters per second. And then the part of this triangle, or the side length that points in the y direction, that's my initial y velocity. The part of the triangle that points in the x direction, that's my initial x velocity. And I can use these ratios. So what I know is that my angle here, that's given as 37 degrees. That was given in the setup here. I haven't really established a problem, but right now we're just kind of looking at how to decompose the initial velocity. Then the relationship between the initial y velocity and the hypotenuse, which is 20 meters per second, is equal to the sine of 37 degrees. So I can say that the initial y velocity is equal to 20 times sine 37, which turns out to be 16. So sine of 37 is right around 0.8. Or excuse me, should be 12. Got that wrong. 12 meters per second. Sine of 37 is right around 0.6. Okay, and so same thing for the relationship between the x velocity and the total magnitude, 20. That's equal to the cosine of 37, because that's the relationship between the adjacent side and the hypotenuse of this triangle. So the initial x velocity is 20 times cosine of 37. And if you work this out, this is 16 meters per second. So cosine of 37 is right around 0.8. And you can look that up. That's what your calculator will tell you. This just comes from studying triangles and looking at the relationships between side lengths. Okay, so this is how we take a velocity that doesn't cleanly break down into x and y and break it down that way. Now we know that in the x direction, the initial velocity is 16 meters per second. In the y direction, the initial velocity is 12 meters per second. And now I can just completely break the x and y parts apart from each other and treat it kind of in the same way that we had treated our previous problems, with a little additional complexity of having both an initial y velocity and an initial x velocity. So let me show you how to work with that for a specific set of questions. So the first question is, how long does it take for this rock? So we're throwing a rock. How long does it take the rock to return to its initial height? Okay, so what does that mean? How long does it take the rock to go up and come back down and get back to the same height that it was thrown from? That's what the question is asking. So that's a question about time. And usually when it's a question about time in problems like this, we're looking for something to do with the y component of the motion, because the y component of the motion tells you something about going up and down here. And what's going to determine the time it takes to go up and come back down to the same height is something to do with the initial velocity and gravity. So let's look at the y equation for this motion. So the y equation for this motion, so the final y position is equal to the initial y position. So let me scroll up a little bit. Plus the initial y velocity times time, plus 1/2 times the a acceleration times time squared. Okay, so do we know these things? I'm going to set my coordinate system such that this green line is y equals 0. So I release the rock at y equals 0, and I'm looking for the time when the rock comes back to y equals 0. So my initial position in y is 0. We just found what the initial velocity was. It's 12. And we know that the acceleration in the y direction is gravity, and it's negative, because down is the negative direction. So minus 1/2, and I'll just let gravity be 10 times squared. Okay, so we now have that the y position at any given time is 12t minus 5t squared. And in principle, we could figure out any position at any given time in the y direction with this equation. We're looking for a very specific time, though. We're looking for the time that y becomes 0 again, because that's the point, that's the height from which the rock was originally thrown. So let's plug in 0 here and see what we get. So 0 equals 12 t naught, and I'm going to say t naught is the time when y becomes 0 again, minus 5 t naught squared. So you notice one solution to this is 0, because if I plug in 0 for time, then I get 0 equals 0, which makes sense because at time 0, the rock is at y equals 0. And we're looking for the other solution, so there should be one more solution because this is a quadratic. So if we cancel out t naught here, then we have 12 equals 5 t naught. So 12 equals 5 t naught. And if I solve for t naught, I get 12 fifths, which is 2.4 seconds. 2.4 seconds. All right, that's the amount of time it takes the rock to return to its original position. Okay, next question to consider. How far does the rock travel horizontally in this time? Okay, so up here I've defined a delta x. So delta x being that displacement from when the rock was released to when it came back to its original height. And we're looking for that delta x here. So when we're talking about horizontal distances, we want to use our horizontal equation. So for us, the displacement is equal to the initial y velocity times time plus 1/2 the x acceleration times time squared. So delta x equals 16 was the initial x velocity we found, and there is no x acceleration. The only acceleration in this problem is gravity, and that pulls in the y direction, not the x direction. So this is our equation for displacement. And we know that the time it took was this t naught, 2.4 seconds. So displacement should be 16 times 2.4. And if you calculate that, you get 38.4 meters. So that's delta x. So ultimately, the structure, the way that you solve these problems is very similar to the way you solve a problem if the velocity is all in the x direction or all in the y direction. It's just a little bit more complicated because of this part where you have to break down the velocity into components and then use both an initial x velocity and an initial y velocity. So I hope that helps, and I'll see you soon. Okay, bye.